Hi, I'm Brian, and this is Lab Group 2A, and we're doing the lab 7 diffraction limited MTF system. And I was the technician for this lab. And starting with our system, you can see we have our laser, and then we have a microscope objective with this 25 micron spatial filter on it, and then we have our collimation lens, just a mirror reflected down this rail. Our aperture set to the smallest setting it can be, and our microscope here is should be at N2, and we're pausing. We'll show you in a second. Alright, so this is part B of our lab, and for this section we were looking at how collimated light interacted with the aperture. So you can see here at the Fresnel number 2 location, you can see that there's a dark spot in the center, and then as we move the microscope down the rail, you can see this changes, and you get a light spot in the center, and these distances decrease in size, and so you can see we have a dark spot again, and then we'll start having some fairly quick oscillations. Alright, so at Fresnel number 1, we found, using this equation for L and this value for our radius of our aperture, we found that we were 962 millimeters away from the aperture. And for our Fresnel number 2, we found that we were 648 millimeters away from the aperture. And then we observed that as we showed the oscillations.
Hey, my name is David Montgomery, and I was the recorder for my team. This is part C of the lab, and basically it's trying to find best focus. This time we did add a component to this part, and that would be the testing lens. It has a very long focal length, and this is to simulate a diffraction limited system. Of course, you don't want it too long because we have a limited amount of rail, and if it's too long, we won't be able to get the correct Fresnel zones. The Fresnel zones we are concerned about are the 2 and -2, which correspond to the -1 and 1 wave defocus. Basically, if you look at the system right now, we have it at +1. It should be mentioned that the -1, I'm sorry. Okay, so in this lab, we were also concerned about the aperture size, and later we would compare it with D, which is the distance between the -1 and +1 wave defocus. To find best focus, we basically find the -1 and +1 values, find their distance off the rail, and then average them to find best focus. Pause.
Hi, I'm Steven, and this is part E of the lab. What we were trying to do in this part is measure the profile of the beam at both best focus and -1 and +1 defocus. So how we did that is previously in the lab we were able to find best focus by finding the dark spots, and we used the dark spots because those are easier to see. So we found each dark spot, and then we moved the microscope a distance from, we averaged that value, moved it from a distance from the dark spot to the best focus position. Then we turned off the laser because we don't want to burn our eyes out, and we put the slit in. And since we know the microscope is imaging a distance away of, at the focus of the microscope, we can focus onto the slit. And when we focus on the slit, we know that the slit should be at the position where that best focus or plus or -1 defocus. When we did that, we took out the microscope from the system, and we added the detector. And we profiled across the entire beam and took readings, and we'll show you the readings in a second. I did forget to mention that the way we wanted to make our slit width exactly 1 over the cutoff frequency, and we accomplished this the same method we measured our aperture size by putting the microscope back into the system and using the translation stage here to measure the distance the slit is opening, because it's obviously too small for a ruler, if you will. Thank you. Okay, so what we expected to see was a Gaussian at best focus as a profile, and sort of this shape at the plus and -1 defocuses. Because at best focus is just the normal Gaussian profile, but at plus and -1 defocus we're going to have a dip because we have a dark spot in the center. The reason why it doesn't go all the way to 0 is because we're a slit, and we are actually taking, we're integrating over the upper values, which still have light in it, but it won't be as bright as this. Also, even though these show the same intensity, this should have a higher intensity peak. Thanks. So this is what we actually came up with. Now, the best focus does kind of look Gaussian, but the other two don't look as we expected. We were not able to figure out why. We redid the lab several times. As you can see, we're actually an hour late from getting out of the lab. We could not figure out why we weren't getting the correct results. So later on in post-lab, we're going to try to use these results and extrapolate the MTF function and the line spread function. From these results, we'll see what we get, but we're not enthusiastic about this because we didn't obviously get the right results.